Today I'm gonna present the paper Blockchain and Stackelberg game model for roaming fraud prevention and profit maximization. Here's the outline of this presentation. Firstly, I'm gonna present the motivation and background of this paper. Then I will move on to the challenges in the current roaming management system and our proposed solutions. Afterward, I will present the economic model based on Stackelberg game theory and the results of our numerical experiments. Finally, I will give a brief summary and future research direction. The motivation for research is that fraud tech has been causing significant losses, more than $22 billion annually for mobile service providers. Among different types, fraud, roaming fraud is the most common. Typically, a fraudster clones or steals SIM card in a country and move to another country to use them. And because of a long delay of up to 4 hours in the data exchanging between the home network and the visited network, it takes too long to detect these frauds, and as a result, it can cause losses up to 40,000 euros in some severe incidents. Now I will provide some fundamental background. Blockchain has recently emerged to be an effective solution for data management. Several organizations such as Deutsche Telekom, SK Telecom, IBM, and Enterprise Ethereum Alliance have proposed blockchain solutions for roaming fraud prevention. However, these solutions are still under development and facing some challenges. In a blockchain network, the data added by the consensus of majority of users. For example, in the proof of work consensus mechanism, the user competes with each other by using their computational power to solve a puzzle, and the player with the higher computational power will have a higher chance to be selected to add a new block to the chain. And in the proof stack consensus mechanism, the user with a higher stack will be more likely to be selected. The stack here is the number of network tokens to assemble the number of coins in a cryptocurrency network. Most of the current blockchain networks are employing the proof-of-work consensus mechanism. However, this mechanism wastes a lot of energy. For example, Bitcoin uses more energy than many countries, and it also has a significant delay, up to 1 hour, so it is not suitable for roaming fraud prevention because we want to reduce the delay. On the other hand, the proof stack consensus mechanism consumes much less energy and has a significant lower delay, around 3 minutes. So the main challenges that we want to address is firstly to reduce the delay in data exchange between the home network and the visited network, and secondly, because user participation is crucial to blockchain's operation and security, we want to incentivize the user participation. To address these challenges, we propose two solutions. Firstly, we develop a proof-of-stake-based blockchain framework for mobile roaming service management. And secondly, we propose an economic model based on Stackelberg game to incentivize user participation in the blockchain network. I will present a bit more details about challenge 1. As you can see in the current roaming system, when a subscriber finishes using the services, the visitor network will send the call detail records to a data clearing house, which will then process and send these records to the home network so that the home network can pay the visitor network for according to the roaming agreement. However, the transmission of these records takes too long, up to 4 hours. To address challenge 1, we propose a blockchain-based roaming system. In this system, firstly, the two networks will form a roaming agreement as a smart contract on the blockchain network. The smart contract is a user-defined program that will be automatically triggered when the conditions written in it are met. So when the subscriber finishes using the service, the visitor network can send the transaction containing the data records data to the smart contract, and then the smart contract will automatically trigger the home network to pay the visitor network. Our system has several advantages, such as much smaller delay, because the delay now only depends on the delay of the blockchain network, and it will be around 3 minutes if we use the proof stack mechanism, and no middleman fee will need to be paid to the data clearing house. I will now explain why we need to incentivize user participation, because in a blockchain network, the majority will decide which data will be added to the chain. So if an adversary can control more than 51% of total computational power in a network, or the 51% of total stacks in a proof of stake network, the adversary can control all transactions in the network. So to mitigate, we need to attract more participation, so that it's harder for the adversary to control 51% of the network. In a proof of stake network, the reward for user participation is determined by this formula. It is determined by the proportion of stakes that the user invests in the total stake of the network, and multiply with the block reward, which is a number of coins, for example, in the cryptocurrency network, and it is set by the blockchain network operator, and minus a fixed cost for participation. This cost is for maintaining and setting up a connection to the network. As you can see from the formula, if the block reward is too low or the cost is too high, the reward will be very small, and so the stakeholders will not participate. But and if the stakes is too small, it may also take too long for the stakeholder to earn the reward. To address the challenge, we propose to use stake pool. In our network, the mobile service providers can create a stake pool, and the pool will participate in the consensus process as a single stakeholder, and the mobile users can invest stakes to the stake pool, so that they can share the operational cost, and also they had a higher chance to be selected to earn the reward. And when the pool earn a block reward, it will charge each stakeholder a small fee alpha before dividing the reward to the stakeholders proportional to their invested amount. The stakeholder reward when invested in the pool is determined by this formula. As you can see, it's proportional to the stakeholder stake in the total network stake minus a small fee, and there is no fixed cost. So to jointly maximize the profit of the stake pool and the stakeholders, we introduce the Stackelberg game model. In this model, the stake pool is the leader, which will make the first move by announcing its fee alpha in the first stage. And in the second stage, the stakeholders are followers, which will then decide how much stakes to invest to the stake pool. Then we will analyze the follower strategies to determine their best responses, and then using backward induction, we determine the lead the optimal strategies. In this game, a follower has the following possible strategies. First is to only invest stacks to the pool. Second, only to self-mine. Self-mine here means that they will participate in the consensus process as a single stakeholder and compete with the pool. And thirdly, invest next to the pool and self-mine simultaneously. And finally, do not invest anything to the blockchain network. However, we prove in the following theorem that a follower-based response is to either invest on its budget to the pool or use on its budget to self-mine. Based on the two theorem, we can determine a follower-based response. As you can see from the function, if the pool fee is higher than the threshold Ti, the follower will invest nothing to the pool, which means it will self-mine. Or if the fee is lower than the threshold, the follower will invest on its budget to the pool. This threshold depends on the fixed cost of the stakeholder, the stack of the pool, the budgets of every player, and the block reward. And as you can see, because for every fixed fee of the pool, we have a unique response from each follower, so the sub-game equilibrium is unique. Based on the follower-based response, we can determine the leader optimal strategy. In this game, the leader strategy is to determine the level of the value of the fee alpha, so that it can maximize its payoff function as given in the following formula. And we prove in the following theorem that the leader optimal pool fee alpha is equal to one of the follower investment threshold. Then we conduct numerical experiments to firstly examine the follower and leader strategies, and secondly we simulate a 1000 followers game to examine the impacts of the budget and fixed cost on the leader profit. This graph presents the followers' best responses. As you can see, for each follower there is a investment threshold, and if the fee is higher than its threshold, the follower will stop investing stacks to the pool. This graph illustrates the follower utilities. As you can see, the follower utility function will decrease as the pool fee increases. However, if the pool fee increase past the follower's threshold, the follower utilities become a constant, because at this point the follower will stop investing stacks to the pool and switch to self-mine. This graph shows the leader utility function. As you can see, as the leader increase the pool fee, the leader utility will increases. However, when it increase past the first threshold, the T1 threshold, its utility will drop, because at this point the follower one will stop invest to the pool. And similarly, when the pool fee pass the threshold 2 T2, the follower 2 will stop investing to the pool, and so on. And as you can see from the graph, the optimal leader strategy will be to increase the pool fee up to the threshold 4 T4. At this point, only the follower 4 and 5 are still investing in the pool. The 3 others follower had stopped invested. In the second game, we simulate a 1000 followers game to determine the effects of the budgets and fixed costs of the players on the profit of a leader. As you can see from the graph, a follower with a higher cost and higher budget will give the leader more profits. However, if the budgets are too high, the follower will stop investing to the pool, and they will switch to self-mine instead. So in conclusion, in this paper, we have proposed a blockchain-based system to address the current roaming flow problem. And we have also developed an economic model based on Stackelberg game theory to incentivize more users to participate. And moreover, we have proved the existence and uniqueness of the subgame equilibrium and also we proved that the leader optimal strategy, because it depends on the threshold with a constant. It can be straightforwardly determined. And for future research direction, we recommend to consider multiple stack pools in the blockchain network. Thank you very much for listening.